In video number 40 of the Foundations of Computational Economics course, we will do a lot of practical work. We will continue developing the Deaton's class and add to it the new methods which are needed for treating consumption choice as a continuous choice. In particular, the plan is to add the implementation of the Bellman equation with non-discretized choices for the starters. Then we can add we're going to add the early residual calculator and the time iteration solver all together. And then, with early residual calculator, we can calculate the measure of accuracy of the solution, and we'll be able to compare different solution methods and solutions that they provide according to this accuracy measure. And that's basically what we should do afterwards with this squared early residuals. We can try different interpolation scheme, and so we can compare discrete versus continuous choices or treatment of the Bellman equation. And then finally, time iterations. Okay, well, let's get to it. So here's the code. I'll switch to the normal notebook layout right away. We're going to start with the code that was copied from video 36 on the simulation or simulator. So here we already have in the class, this is Deaton's class. And so here we already have the simulator. Okay, let me run this and run a couple of examples here. As you can see, the example is solving the Deaton's model using VFI and plotting the convergence. It converges in fairly low number of iterations, so that must mean that beta is not too close to 1. And then it produces a number of simulations initialized at what the fractions of wealth starting 15 lines starting spanning the space between 0 and m bar. M bar is 10 over here, and so this will serve us as the standard simulation, standard check, I would say, for the solver. Now I also wanted to include the cake-eating problem as a special case, and we have some provisions for that. If you remember, in the calculation of the next period wealth, we are actually checking if the number of grid points is greater than 1. And the grid points, the quadrature points, I meant to say. So if the number of quadrature points for the calculation of the expectation in the Bellman equation is greater than 1, then we actually compute quadrature. Otherwise, we just skip income altogether. So quadrature number of quadrature points equals 1 corresponds to no income case. Because even with sigma equals 0, the expectation of the log normal distribution will be 1. So we can easily have the non-stochastic income being equal to 1, but not to 0. For the cake eating problem, we want that case as well, and this is probably a hacky way, not the best way to include this case, but it allows us to reduce the number of parameters and attributes in the class, and will do for now, at least for now. And so this number of quadrature points equals 1 corresponds to the cake eating case where there's no income. And we should also, interestingly, we should also set the gross return, the R parameter, which is called just R, to exactly 1, right? So there's no gross return to the cake. Okay, here we are. So this is the cake eating problem version of the consumption savings problem. And here's the solution. We know that the analytical solution is a straight line starting at the origin. So this is not too bad, actually. Well, we're using 250 points for the grid of choices. And here are the simulations from this model, which we haven't seen yet. And you can see, actually, over here, you would expect these lines to be really smooth, right? The simulated consumption lines, but there are some artifacts right around here, which tell me that the solution has some wrinkles, right? And they're probably around here. Well, you can see the wrinkles in the solution graphs, which are, of course, due to the inaccuracies in our implementation of the discretized Bellman equation, which cannot find the optimal level of consumption at the infinitely small increments. Okay, so this is our starting point, and according to the plan, the first thing to do is to implement the Bellman equation with non-discretized choices. Okay, so before we go into that, there are some things to clean up in this existing code from my point of view, and here's the logic. Remember, we have the quadrature points to calculate the expectation with respect to the random income in the next period, and we set it up correctly or nicely so that when the n quad attribute of the class is changed, or equally sigma parameter or attribute of the class or of the object is changed, then the special methods are fired. The setter methods, so the setter, this one, right? The setter for the n quad and the setter for the sigma, and they invoke the quadrature setup internal method that recalculates the quadrature points and the weights. And when we coded up this Bellman, discretized Bellman, the idea was to keep everything vectorized and to organize the code so that the calculation of the maximum of the inside of the Bellman equation is done by just applying the Amax operator along the appropriate axes, which is the axis 0, so that we have choices in the axis 0 in some three-dimensional array that represents the maximand. This one rather, but it is also a three-dimensional array, which is the maximand of the Bellman equation. Well, now of course we have to compute this maximand as a function that we have to pass to the numerical solver, and therefore the mechanics are going to be different. It first of all cannot be vectorized in the same way as we are vectorizing things here. And in particular, now we don't really need the three dimensions in any of the arrays, because we're not going to have choices along any of the dimensions. The maximand as a function will be optimized sort of point by point, similarly to how we did in the k-kitten example. What is it? NVIDIA 38. Right. So that implies that we don't that we need now to try to accommodate the schemes where where three-dimensional arrays work together or in the same time with two-dimensional arrays in the same class, and that calls for some reorganization of the code, which is totally fine. This is natural to develop the code that works in one case and then sort of go back to this code and improve it and make it work for a different case. That's essentially code refactoring. So here's the proposition. First, we will be changing the code here in the class. And it is always a good idea to do it incrementally so that we can remove the changes and be able to check whether the old version of the code and the new version of the code produces exactly the same results. And I'm not going to do it in this video because it's going to take even more time. I expect this video to be quite long already. And so we'll do it in a terrible manual way. So here's the results. Here are the results of the code as it is now. And now I'm going to be changing the code, and I will expect to get the same results. I'll just copy the cells here, which around this test results or test cases. And I will keep the output of this previous run intact, so that we can always compare it to the output of the original code. Okay, so first thing to do is we're going to keep the quadrature points and weights as one-dimensional arrays. The idea under this change under this refactoring of the code is that only the methods that require this multi-dimensionality of the objects work with that. And the methods, say the Bellman equation in the continuous version, does not require that. So all the methods outside should work with any dimensionality sort of seamlessly. And then the responsibility of creating the right dimensions of the objects will be with the methods that invoke the parts, the common parts of the model, right? Like next period wealth calculator. And so we will not shape the quadrature points such that they are in the third dimension. We'll just keep it as a one-dimensional array in the beginning, and then reshape it as needed. Okay, and now for the next period wealth, I'm just going to copy this whole function so that we have a chance to compare. And let's call this one old. And this one is going to be new. And I wanted to always accept income as the third argument. As the third argument in the function. Now, the logic here is that we should not worry about the dimensions of what's happening here in this function at all, and perhaps only keep the logic of this one quadrature point special case. The comment is wrong, but let me keep it. Okay, so here in the standard case, if the number of quadrature points is greater than 1, then we return the next period's wealth as implied by the model. And the idea here is that if we pass M and C and Y of different shapes, then the broadcasting should happen here automatically. The self R is a scalar, and then it's going to be the responsibility of the caller of this function to make sure that the arguments are of the appropriate shapes. And the only thing here is that I don't want to put just 0 here, just in case I want to make the NP array zeros with the shape equal to the Y shape. So to make it completely robust, the result should be not dependent on whether this is a special case or not. The result's shape should not depend on whether this is a special case or not. It should just replace incomes with zeros. Okay, and we don't need any of these lines. See, now the next period wealth becomes a really straightforward function. It's only about economics. And this is how it should actually be with this part of the code, which is about the structure of the model and not about the solution methods. And that's why I think this is going to be much cleaner and straightforward. Now, this is exactly what we had for the case where we wanted to simulate the data, right? So we've added this y equals none and the condition on y equal none or not. If y was given, then this is exactly the return that we had in the old version. And so the simulator should work just as is, but we need to update the Bellman discretized, of course. So just to make sure, let's search for where the next period is wealth is called from. So this is Bellman, this is simulator. Okay, so what's going to happen in Bellman? This is a quite deep refactoring of the code, but we can do it. The idea is still the same. We will have to have the three-dimensional array, so the structure of this code is going to be just as before. The only thing is now that we want to do all of this reshaping and making sure that the variables have the right shape right here in the Bellman equation. Let me make a copy of this as well, just to be able to compare to what we had before. And once we confirm that it's working, then we can delete the old copy. Okay, let me start with creating M and C and Y. Okay, I want these to be the arrays of the appropriate shapes. So for C, we are using the grid over for the choices, the CH grid, and we want it to span the first axis in the three-dimensional array. So I'll say axis 0 choices. For M, we want the grid over state space, and we want it to span the second axis of the three-dimensional array. So it's not a really row vector, it's axis 1 states. And what's the difference? Well, this is a three-dimensional object, and it is like a row vector, but it also has the third dimension, which is just equal to 1. And then finally, the y is going to be represented by the quadrature points, right? Because we need to calculate the expectation here. So we need the quad p. And this is now a one-dimensional array when it's initialized. I'm here. So I wanted to span the third axis. So I'm adding new axes in the first and the second place, and the third is going to be spanned by the data. Quadrature points. Okay, now let's do a bit of a test down here. Insert cells. So let's see. Instead of self CH grid, I'm just gonna say a range of say we have 4 choices. Let's have 3 points in the state space and say 2 quadrature points. Okay. It's invalid syntax. Yep, that's better. And now I want to create something like C plus M. Okay, let's just create that as A and print a shape. I guess I want the separator to be a couple of new lines. Okay, so look at this. The C is just a range, right? 0, 1, 2, 3, but it's a 3-dimensional array with a shape, C shape, with a shape 4, 1, 1. If I add C and M, that's going to gain one additional dimension, namely the second dimension, because of the broadcasting that is done in NumPy. So now it's like a matrix, but it has the third dimension, which is just unitary. And finally, if I do C plus M plus Y, then I get a complete three-dimensional array with dimensions 4, 3, and 2. with the number of elements 4, 3, and 2 in all the three dimensions. So this is all due to broadcasting, and this is what we are relying on here. It's just that we are now taking the broadcasting ID into three-dimensional space. Okay, this is the idea here, and now let me start copying lines from below. Now, how do I scale values of choices? You know, all of this will result, let me copy this line here. All of this will result into my, the next period wealth, being the three-dimensional array. The way I just showed, the way I just showed. So m, c, and y, this is going to be passed to this calculator that we just corrected, right? And all it's going to do is just going to calculate this numerical expression, and because of broadcasting, this will have this will return a three-dimensional array. All right. What's next? Next, it's pretty much the same thing. Let me comment these out. So now that we have the three-dimensional array of next period wealth, we can interpolate the value function using this, except where's the interpolation function? Oh, okay, we are calculating this here, the interpolating function, and then we interpolating using m1 as points of interpolation. So v1 is now a three-dimensional array with the needed arrangement of axes. And the EV is the dot product as before to the quadrature weights. So this is now the expectation of the value. Now mx is the maximum that we're interested in. That's now the utility of c plus self beta times EV. So here we have a bit of a problem, because C is three-dimensional array according to this. All right, even though it only has data in first dimension, the utility of C calculated at C is going to be a three-dimensional array, and we want to add the two-dimensional array here because EV is now just a matrix. So to correct for that, we just want to say that we need C to be a two-dimensional array for all choices and states. So we'll take the first two dimensions of C as they are, but only take the first element in the third dimension. So this is like taking a slice, the first slice in the third dimension, and this is now a matrix, right? So C here is the matrix. And let's check this here. So A is a three-dimensional array, as we've seen. Now if I say this, and print the shape as well. Now it's just the first slice, right? Let me do both, actually. Okay, here's the three-dimensional array. And remember that it's the third dimension that has two elements. Now we want to take the slice of this column, this column, this column, first, and put them into a matrix. So 0, 1, 2, 3. It's going to be put into matrix like this, right? The first dimension is actually, the first axis is, like elements like so. So these elements will be put into the 0th axis, the first dimension, and then these elements like this will be put into the second dimension, like that. In any case, it produces a matrix of 3 by 4 if I just slice it in the correct way. Right, so this utility is now the matrix, and then this is a matrix, and this is calculated as it should. Let's look at this other next condition. C greater than m. That needs to be a matrix of booleans, of false and trues. But so far, the C and m are three-dimensional arrays, so we have to do the same trick essentially. We have to cut the third dimension off of both of these arrays. And now, because of broadcasting, this comparison operator will produce the matrix of booleans. And finally, we can do the usual axis 0. And over here, though, again, this C is a three-dimensional array. So instead of doing this, we want to do that on the first layer of the third dimension. And I'm running out of space for the comments. According to Pepe, there should be 2 spaces before the comment in the line. Okay, so all of this seems to be fine, and I think it should run now. Okay, except for that unfortunate mistake here. Right, and let's try to produce a result. It doesn't work. What's wrong? Index 1 out of bounds for axis 1 side. Where's this? This is in solve plots. Solver func in Bellman, and in particular here. Index 1 is out of bounds. Oh yeah, of course. So before it was the matrix that we had to take the values from. And these are the argmax, and I wanted to take argmax in each column by itself, and therefore we had to have this range here. Now C is a three-dimensional array, but data is only in the first dimension. So in fact, we had enough spaces here. Okay, let's line up the comments later. So I only need to look at the first dimension when I take out the correct indices. So let's see. Do we get the same result as here? It seems to be more wiggly over here, isn't it right? So it's not exactly the same one. Let's see what's missing. Here's the discretized Bellman, which is new, and here's the old one. The missing thing, as you've probably thought of already, is this normalization that ensures that C is always greater than M, the corresponding M, so that we don't waste the points of the state space, of the choice space. And this is what we haven't done yet here. So how would we do it? The consumption levels is a three-dimensional array with data only in the 0th axis. But we have to normalize according to the values of M, which is in a different axis. So we need to have a matrix here that would be have different levels of C in different columns. But as we want to bring this all to the 3 dimensions, we will do the following trick. So first of all, in order to do this normalization, which is important, okay, we will expand C itself into all 3 dimensions by doing the repeat operation. And so this means that I'm going to take the C, which is the vector in the 0th dimension, although there are 2 more, and I'm going to repeat it along the first axis. How many times? Well, in the first axis there is the n-grid elements, right? So I should do the n-grid repetition. And then this is creating a matrix, but I also want to expand it into the 3rd dimension according to the number of the number of elements in the 3rd dimension. So that's that number of elements is given by the n quad, and the axis is 2. So of choices. Now, what this gives me is the ability now to change different values of C in all these 3 dimensions. And by the way, this doesn't change anything, right? Because we've done what broadcasting rules would do for us anyway. So this operation basically just wastes space because we are using more memory after this repeat, and it also does some memory allocation, which wouldn't be necessary, strictly speaking. But what we want to do is we want to say that C should be now multiplied with the value M, which is the state space, divided by self M bar. Right? This is this normalization that we did here. And let's do it in the same fancy way by doing the multiplication and assignment in the same time. So we are multiplying C with the M bar. Now M is a three-dimensional array and C is three-dimensional array. So it's possible to do this element by element, and M will be broadcasted in the dimensions where it has just one single element, which is the dimension 0 and 3. And so M will be broadcasted along those dimensions where it has the same values, essentially, right? And so this normalization should work fine. Now, is this all that I had to do? Now, C is a three-dimensional array, and we're throwing the last dimension here, and we're throwing the last dimension here, but not the previous two. So this is like a matrix which will not have the same columns of C. They are now normalized, but this should work fine because this is just a matrix compared to a matrix. And what about this one? Well, this one now is wrong, right? Because C does not only have data in the first dimension, it has now matrices repeated in the third dimension, but we actually need to look at the matrix. And so this range n-grid needs to be returned back. It's good I didn't realign the comments. Okay, now I expect we should get exactly the same, and obviously we don't. So exactly the same answer as here. That's what we should have gotten, but something is very wrong. The value function is different. Okay, let's think about what could go wrong. And of course, what's wrong is that we are updating the C before actually calculating the next period wealth, which should be, of course, reversed. Okay, let's see. Now we should expect to get exactly the same answer as here. And we do. Wonderful. And the simulator also works. Okay, let me clean up the code and delete all the previous versions. As I said before, to do it correctly, we should have set a number of test cases and compared the previous version to the new version more rigorously than what I did. But this is for the in the interest of time. Let's run it again. And what about the cake eating case? Also works and produces identical results. Okay, I don't need this cell anymore. And we can continue to the main task of introducing the new Bellman equation, which implements the calculation of Bellman operator without discretizing choices. Okay, so to proceed with that, I'm just gonna go to the lecture code again and draw inspiration from this code of the cake eating problem we had in the lecture, and use this code here as a starter. We will have to have a new Bellman implementation. Let's call it Bellman continuous. It should have exactly same inputs, right? Because this is just a Bellman operator, a new implementation, but it should have exactly same form. And this is what's beautiful about it, because it doesn't matter how what's the algorithm for solving the whole problem. the Bellman equation is a Bellman equation, and so we can actually use either of the two Bellman equations with the same value function iteration solver. Okay, let's make sure that this copied Bellman continuous works with the consumption savings problem. Let's see. So first, interpolation. Well, interpolation is done here differently from where we've copied it from. Interpolation can be adjusted, and so I have to call self interpunc with the corresponding data, and this is the data that we need actually. Okay. Now, I'm going to change the style of these comments as well. Relation function for V0. Now, allocate space for the policy function. And we should actually also allocate space for the value function that we will compute in a different way. This will not work here. And it will not work because of the this is a vectorized version which we organize differently. Let's do a separate special treatment of this C0 case, but let's not forget it, so I don't delete it yet. For the value function, and then for I in range self and grid. Let's actually do a more Pythonic way of enumerating the grid. And this is now optimal consumption for a given amount of wealth, M. Maximand is actually not needed here, as I thought, and I was right. So all we need to give to the find C function is the interpolation function that represents the value of the next period value function. Okay, so that allows us to calculate that, and we will also need to calculate the value. And let's see how it's done a little bit later. Or actually, we do know already. Don't forget the negation. It's just going to be the maximand calculated at this just computed level of consumption. Self-grid. No, instead of cell grid, we have the single point M, and the interpolation is also needed. Okay, and then we can return. All right, so the two nested functions, as you remember from 2 videos ago, I hope, is the solver that finds the optimal consumption level for each particular point of wealth, and this solves the optimal consumption for given wealth M. And the interpolation function, okay. Now the options here are self, max, iter Bellman, and toll Bellman. We need these, and they have to be new attributes of our class, actually. So let's introduce some new attributes here. What is this max iter for continuous Bellman? Operator. And this is the tolerance. So these are the tolerance and the maximum number of iterations for the internal optimizer in the continuous Bellman equation. And I don't know, let's make it a large number so that we don't have to come back to it. And tolerance should be fairly tight. But of course we can change it. We can change it on the fly. Okay, so this new attributes will be available in the in here in the continuous Bellman. And now we want to minimize scalar. Oh, by the way, where's this function coming from? This function is coming from SciPy Optim. Oh, Matplotlib inline is also good to have here. Okay. Right. Okay. Now, if is the cells that we need arguments m interf f right bounded self epsilon optimal opt. The only thing which is which shouldn't be forgotten is this special case. So if m is less or equal for some reason, oh, self epsilon doesn't exist. Let's see where self epsilon is coming from, or where is it? It's right here, epsilon. So it's basically the first point of the self grid, and we can just use that. Instead of self epsilon, I'm just going to use self grid. We don't want to look for consumptions too close to zero. But if the amount of wealth is that low, then let's just return m as the heuristic solution. So now we've taken case of this, and I can delete this line and copy that guy in line with all the rest of the comments. Okay. Now, if we successfully found the optimal consumption, then it's good. Otherwise, instead of returning this, let's erase the error, and this is going to be a runtime error, and we can say that the Bellman failed to find optimal consumption. Okay, the last thing to do is to update the maximant. And here we can look at the Bellman discretized and see what's going on there. And come back to all this complications with the third dimension and three-dimensional objects. So what we need to calculate here is the maximant, which is this, the mx, right? The mx, and we also know, because of these bounds, that the infeasible choice will never be encountered. Okay, so we also know that both C and M are simply scalars. So the task becomes much simpler, actually. Let's see. We need to calculate the M1. And for that, we already have M and C. What about the quadrature points? Well, we can just... because M and C are scalars, then we can pass quadrature points as one-dimensional vector instead of y, and what we get out is what we get out is the vector of next period wealth. And then we can immediately do the interpolation, because the interpolation function is already given. So this is value function the next period wealth, and this is going to be a vector as well. We still have to do the dot product, and let me just keep it as a dot product, although we could do the matrix multiplication here as well. It's now a scalar. And finally, we can calculate the maximand by calculating the utility. C is a scalar, so just the utility of C, and self beta times EV. It's all just scalars. And then we can just return mx. Don't forget the negative one. Oh, it's good. Don't forget the negation, because Python, the SciPy optimizer, is looking for minimum, not the maximum. Okay, so this should be it for the maximand. And let's see if it runs. Now I want to... Oh, how do I actually invoke this new Bellman equation? This is a separate task now. So if I call Bellman VFI, it's going to call Bellman discretized, and I need some way of switching it to the new Bellman equation, new code. And for that, let's treat this as we did with interpolation. Let's have the self, say, Bellman type. And have an additional argument to the initializer. Type of Bellman operator. By default, it can be discretized. And I want to, here's an idea. Let's just have Bellman called in the solvers. This is not going to be the only solver, this VFI. So let's just, in the solvers, call Bellman. Well, Bellman method doesn't exist, so how is it going to know what to do? Well, let's actually create a new property that would tell... or that would remember the function that should be called for the Bellman operator. So I'm gonna copy this dynamically updated properties, and the property I called it Bellman type. And here what it's gonna do. For the Bellman type parameter, okay, so this is going to be a Bellman type. What do we do on return? On the getter, actually, let's just do the help of self Bellman, and make sure that the self Bellman or Bellman operators have good. Discretized choice with continuous choice. Choice. Okay, but if we want to set the Bellman, then we'll have some code here. So if, oh yeah, and by the way, we set it to some value. If value equals discretized, we do something. Elif value equals continuous, else raise error. Runtime error. Unknown Bellman type parameter. And here's the magic. We can just say self Bellman, and we want to create a new attribute of our own class. And so if Bellman is set to discretized, then we can say that self Bellman is simply Bellman discretized, or self Bellman discretized rather. And note that I'm not going to have any brackets or anything here. So this is just a function, and we're going to create a new method for the class, which is going to be called Bellman, and it will be a function as well. Which function? Well, this function. And then, of course, for the continuous choice, we're going to have this to be continuous. And now, once the type of the Bellman is set, then by calling self Bellman, we will be effectively calling one of the other function. Let's see. So nothing should change here, and doesn't seem to change. It's still exactly the same as this output that we had in the very beginning. But now, if I say here Bellman type equals continuous, we should now involve the new code, and it produces a bug, which produces an error, which supports the fact that we are now calling a new code. Wonderful. Okay, so what's the problem here? Solve plot, solver function. It's the solver that is not working, Bellman, and returning v1 is the problem. Okay, that's simple to fix. I guess we should call it capital V1. It's also here. Let's see. Oh, it seems to be working. Let's see if it produces the right result. Seems to be similar to this, but not identical, right? Why is it not identical? Well, it's much smoother. That's because we're treating choices now as a truly continuous variable, and of course we should expect higher accuracy, although longer runtime. What about the cake eating version? It also seems to be working. Of course it's the same as before. I need to say that we now want to use Bellman continuous. And see, it's taking time. Now, each bar here appears on the iteration of the value function iteration solver. And it's taken some time. Let's see what we get. Well, we get is it better? There are still some artifacts here that I can see. But probably it's not worse. Well, there are more artifacts in the solution, for sure, than in the solution of the continuous version. So this is definitely cleaner. Okay, what's next? Next is the earlier calculation. We should do that. And so where do we start? Well, let's start by opening up the lecture notes from 39 and find the equation that we actually need to implement. The early equation and the Kalman-Refit operator. And so it's right here. We have to calculate the early residuals, so the difference between this left-hand side and the right-hand side. And in the right-hand side, we are calculating the expectation of the marginal utility of the policy computed in a particular point. And that point, of course, is very much like the points in the Bellman equation. that we've computed before. Right. So let's think about the inputs and outputs of this new method, the early residual. And let me start coding it up. Maybe somewhere here under Bellman's. Def Euler residual. So self is the first argument. The Euler residuals. Okay, where do we have to compute it? See, we will have to pass the policy function, which enters here, sort of the previous iteration policy function, which is the input of the operator, of the Kalman-Refit operator. And then we want to compute the solution of the equation, which is the C prime, for all different points of M. So I think we have to take the points C and M as input, and then the policy function that enters into the left-hand side of this early equation. So computes the early equation for given points M and C, and given policy function that enters into the right-hand side. Okay, and so how do we do it? See, it's going to be very similar to the computation of the expectation. So I think we can draw inspiration from the Bellman equation calculations. And probably the Bellman equation, which is discretized. And also we have to think about the dimensions of this matrices. So what are the C and M? Let's just write a comment here. Assume that C and M are either. So we have to calculate, when we're doing time iterations, we will have to solve this as an equation, right? So we have to solve the equation that the early residual is equal to 0. And we will be calling this equation as a function with a fixed m, a scalar, and different values of c. So we have a function in c for different values of m. So they can be scalars. But we also want to calculate the accuracy measure, right? And here's the beauty, that we can reuse the same earlier residual method to calculate the accuracy measures, but then we want to calculate this probably on a grid of M's and a grid of C's. So let's also support that case. So assume that C and M are either scalars or one-dimensional arrays of the same size. And I don't really want to put an assert here, just because this is going to be called as an equation many times when we solve an equation. And so let's try not to put more code here than we need, just to save time. Okay, so for both scalars and arrays, I guess we should differentiate between them, so between these two cases. But, well, let's think about that. So what should happen? Well, first let's calculate whatever is inside of this bracket that goes into the policy function. I'm going to assume that policy is just the function values which are calculated on the state grid, as all of our value and policy functions. Okay, so I think we can copy all of these lines and work with them. Okay, so C is going to be given, and it's either a scalar or an array. M is going to be given, so Y is going to be the set of quad points. And now to be able to do the dot product, we should keep the quadrature points in the second dimension. But here it's just going to be a dimension 1, right, at most. It's either a scalar and dimension 1. So we actually have to do the branching here. So let's, why? Because if C and M are scalars, then the quadrature points can be just a one-dimensional vector that we then multiply with a one-dimensional vector of weights over here in the dot product. Where's the dot product? Here. To calculate the expectation. So this is the weighted sum as before. But if they are one-dimensional arrays, then we have to create the matrix, and then the quad points have to be in the first dimension. Okay, so I'm going to check if C is ND array, and that's going to be different from scalars. Scalars are just going to be floats, right? But if C is an ND array, then and we'll have to have new variables for C and M then. Okay, if C is an ND array, we want to make sure that C is in the first dimension. New axis. And I put here axis 0 choices. And same thing for M actually. Okay. And else we assume that they are then scalars, and then this can be, oh, by the way, can I just save a line here and do it this way? Just to be a little bit more fancy. And then I can copy these two and just say that if they're scalars, then we don't change anything about M and C. And the quad points can be just one-dimensional array. Okay, fine. Now, what about this normalization of C that we're doing in the Bellman equation? Let's assume that when we calculate early residuals, then the C is never going to be larger than M. And we can ensure that because both when we're solving the equation, we can adjust the upper bound. And when we're solving for accuracy, then the policy function is not going to be ever exceeding the M. Okay. Now, if we now call the next period wealth, then we will get back either a one-dimensional array, one or two dim arrays with quad points in the last dimension. That's correct. That's exactly right. And here we have the interpolation function, and we want to interpolate on the cell grid the policy itself, right? Policy. For next period policy function. And we can interpolate, this is going to be C1 now, because this is a policy function, and we will find the consumption in period 1. Now, let's be careful here. So we find the consumption in period 1, but now we have to have the marginal utility of which we are calculating the expectation. So there must be a new line here, U1, or MU, should I say, marginal utility. And how do we calculate marginal utility? Marginal utility of C1. And now we can calculate the marginal utility dot product with the quadrature point weights, and thus we're calculating the weighted sum of this marginal utilities for all different possible values of income. And this becomes the expectation, right? And once that is done, then the right-hand side simply equals self beta times self R times EV. Well, let me just copy this actually. and then we can say right-hand side of Euler equation. All right, so we need marginal utility. This is not coded up yet, and let's go back to the beginning of the class where we have this model parts, the fundamentals of the model. And the marginal utility is going to be calculated of the level of consumption. And of course, for log, it's just going to be 1 over C. And if we change the utility function later on, then we can also change the marginal utility. They're close together. So hopefully we will never have a bug related to that. Okay, marginal utility is done. Right-hand side is done. Left-hand side of the Euler equation is given by the marginal utility of C itself, isn't that right? So here we have marginal utility of the C, which is the points where we want to calculate the Euler equation. Now, is it C or C not? It should be just C, right? So this is either a scalar or one-dimensional array. So if it is a one-dimensional array, see the dot product will return a one-dimensional array, and we want to keep the right-hand side and left-hand side of the same shape. And then we can return, say, left-hand side minus right-hand side. And this is going to be the Euler residual. Okay, let me clean up a little bit here. So axis 0, axis 1. One-dimensional array of quadrature points. One-dimensional, two-dimensional arrays with quad points in last dimension. That's right. Well, what did I do? Press tab, but didn't change any text. Marginal utility in the right-hand side. One instead of 2, but that's okay. Okay, so this seems to be all that we need to do for the Euler residuals. And let's test this function together with the time iteration solver. So let's start coding the solve, say, time iter. And what do we know about this time iteration solver? Well, it's a successive approximation solver, right? So the structure will be just as the solver VFI, except that we iterate on a different operator. But the inputs like max iter, intolerance, and callback, the structure will all be the same. So solves the model using the value function iterations. Now it's going to be time iterations, which is successive approximation of Bellman Equations operator. Let me check if I spelled that correctly. Equations, yes. Callback function is invoked. Yes, that's all right. Now, this will be iterating in the policy function space, right? So instead of V0, I want to start with some initial C0, which is going to be a representation of the policy function. So on first iteration, and assume consuming everything. Well, let's keep that same assumption, but policy, that means that we equate policy to the grid. So whatever wealth you have on the grid, you consume the same amount. That is the amount that you have. Okay, for iter in range, Now, see here, we have a vectorized Bellman, which takes the V0 as a one-dimensional array and returns V1 and C1. We don't have this anymore. So we actually have to loop over the points in the state space. And for each point in the state space, we have to solve the earlier equation. That's how it's going to work. And let's, as before, do the enumerate self grid. And here, C1 of E is something that we need to solve. So solve the equation here. All right, first question is, where is this C1? C1 needs to be allocated. And let's allocate C1 here, allocate memory for it. So create an empty array of D-type float. And how many elements should it have? It should have self and grid. Right, because the size of this vector should be the same as the state grid, because we're calculating the policy, the optimal consumption for every value of the state grid. Okay, so now we're going to be solving the equation here, and now we have to think about which solver to use. Let me go to this overview of the SciPy, optimize, and we have a section here on root finding, scalar functions. Okay, that's what we need. We have a scalar equation. And what's the choice? Newton and Brent Q, where Brent Q is the best choice. The other methods we use for certain purposes, academic purposes. Nice. When bracket is not available, but one of those, then Newton's. Well, derivatives are hard, right, as we discussed, because we, well, actually, looking at this equation, can we differentiate it with respect to C prime? I bet we can. So there's going to be a second derivative of the utility function, which is fine. Utility is analytical. So we could actually use Newton method here to solve this equation. But let's make it a little bit simpler for ourselves and use the derivative-free Brent. That's Brent's method. And the Brent method is actually a nice combination of bracketing, bisection, and additional things, and provides classic so there are some okay, here's some background. Brent claims convergence is guaranteed for functions computable within AB. Wonderful. And so it works on the interval as well. I mean, we could just we could just use our bisection algorithm that we coded up ourselves earlier. But let's try to use the stock solver this time. So what do I need to know? Well, first of all, it's SciPy optimize Brent Q. So let's import that. And we're already importing the minimized scalars, so Brent Q can be imported as well from SciPy optimize. And I want to call Brent Q here. What does it return? Returns a float and the root result. Okay, I probably just want the root that it finds, A and B function, A and B as the brackets. So what is my function? The function is self early residual. Self early residual. Of course, self is going to be passed already. Now, C, M, and policy is what I need to pass to the early residual function. So policy is the previous iteration policy, which is C naught, and this is a vector. Right now, what is M? That's the current value for the resources, and this is what we are looping over. And C is going to be the variable with respect to which we want to solve the equation. Now, the function is returning a number. The function must be continuous, or it must be opposite signs. Oh, this is a good point. Now, as before, there's this args. So the function must be passed as a function. not a call to the function, because what's written here now is the call to the function for a particular c. But we need to pass it as a function. C, the first argument, is going to be called, and args equals this tuple should be added to each of the calls of the function. So here, containing extra arguments for the function. So function is going to be called f of x plus args, where args we're giving. So the first argument will be added as the variable with respect to which we are solving the equation. A and b are the brackets, and so a, this is going to be similar to the continuous Bellman, right? So bounds is cell grid 0 and m. We are solving with this within this bounds. Okay, what else do I have to say? A, B, extol, rtol. Yeah, we need the tolerances. We need the tolerances. Let me go to the new line. We can, as long as there are brackets that define this sort of set of arguments, we can use multiple lines here. So let's do the Bellman. What was that tolerance? We have the additional tolerance for internal solvers here. Max Eater and Tol Bellman. We should probably call them differently now. Tol Bellman. And I guess there is a Max Eater as well. I'm not going to use the relative tolerance. Self Max Eater Bellman. I really want to change the names already. Tol Bellman. 5 matches. Tol Bellman. And replace with Tol internal. Internal solver. Replace all. And what about the Max Eater Bellman? Max Eater Bellman, 5 matches. Max Eater internal. Hopefully everything is right. Max Eater internal, tolerance internal. Are we using these anywhere when we call them? No. And in the Bellman continuous, this would be Max Eater internal, tolerance internal. Okay, good. Back to the time iteration. So Max Eater, self Max Eater internal, tolerance internal. Okay, what else do I need to give to the Brent algorithm? Full output. Full output is false. The roots are returned. Okay, that's what we need. We just want the root. But if it doesn't converge, what happens? So here's this argument here: disp if true, raise runtime error if the algorithm didn't converge. Let's do that. So if algorithm doesn't converge, we'll just get an error. And I think this is all that we need to tell to the Brent queue. So this will find optimal consumption level for given m. Okay. So we found the optimal consumption level, and this creates the, we are looping over all of the possible points of the state space, and now we have the full C1. Let's check whether we've converged in policy function space. So C0 and C1. If callback, there's value here. Let's think about what to do with value. Let's just say for now that value is just none. For the callback, error less than tolerance converged, and here to get ready for the next iteration, we have to update the policy function, not the value function, right? Because this is a successive approximation solver in the policy function space. And then self-solution value, again, value is just going to be none for now, and C1 and return. So this is it. We can start testing. Let me comment these out first, and then say VC equals solve, and this is time iter. Of course, there are some problems. Has no attribute. Oh, that means that I didn't run the code. This main object code. If is instance invalid syntax, I think I forgot colon. Still invalid syntax in brand Q. What's wrong with brand Q? Don't understand. Args and policy. Okay, so inside of args, I can't give named arguments. Well, that's all right. So policy is just going to be C0. Okay, then it's fine. But we still have problems in here. In time iteration, must have different signs. Oh, right. So what's going on here? And this is probably in the first iteration. So as we go through the grids, through the grid of space, the first point is, remember that a really tiny amount, which is really close to 0. And we're solving the model or the equation, the early equation between the cell grid 0 and the same point. So the interval is really not existent. In that case, we shouldn't even solve the equation, right? Then we know the answer already. And this is very similar to what we did here. We had a condition if m less than or equal to grid of 0. Let's do the same condition here. This is really technical. Just say C1 of I equals m. Okay, that's what we did in the Bellman equation. So if we're in the first point, we just say, there is no choice. You just consume everything you have, which is pretty much 0. And else, we have to think about another thing. So let's try it again. And still we have they have to have the same signs. And it's probably not the first iteration. Let me print I here just for testing purposes. We do get 0 and 1, and then we get an error. So the error now appears in the second point of the grid. Well, this is about the solution method itself. Remember, we were saying that the earlier equation only holds for the interior solutions, right? This is a first order condition, but we could have a corner solution. And indeed, in the first point of the grid, the wealth is really, really small, and we know from this graph that when the wealth is really small, it's actually optimal to consume everything. Because you know that in the next period you'll get a little bit of income, like around 1, right on average about 1. So if you have much less than 1 to begin with in the current period, then it's optimal to consume everything, and the solution is really a corner solution. How does that manifest itself? Well, let's think about it. The early residual is the left-hand side minus the right-hand side. Left-hand side is the marginal utility of current consumption. Marginal utility when m is very small and consumption cannot exceed m is really large, right? So this part is really large. You want to consume more today if possible. But if you consume everything, then this becomes really large. Yet, because we have this y, then you know, this is smaller than the left-hand side. We really want to increase consumption today, and we can afford decreasing it tomorrow. Except now we are at the boundary. You know, we cannot exceed more than increase more than to the m. So, in other words, in this corner solution, the left-hand side is going to be large, and the right-hand side is going to be small. And this is the same as on the lower bound of the grid at A. And that's the situation when the signs are the same. What should we do here? Well, the earlier equation does not hold for the corner solutions, and we could have written, you know, the full-blown set of conditions from Kuhn-Tucker, the occasionally binding conditions. But instead, we could just filter out these cases and say, or, you know, what's the answer then? The answer is that the C1 should be M. And so we can just deal with these cases directly. How do we check for that? Well, we can calculate the early residual at the points C equals M and M. So what's the early residual of consuming everything? And now we have to give it the policy as well from the previous iteration. So if this is greater than 0, right? So we want to consume more, but we are already at the boundary. C is already equal to M. I can probably make it more explicit. C is already equal to M. Then this is the solution. That's the optimal policy, and we don't need to solve the equation. Okay, let's try it this way and see, do we still get the same thing? Okay. Oh, there was a mistake. So the code didn't update. What's the mistake? Positional argument, false keyword argument. You're right. That's not the way to do it. So I have to say what policy equals here. Yeah. Oh, and now it went away. Right now we are iterating nicely. Let's kill the print. It's printing too much. And run this one again. The model is not solved, but that's because the print is here. So now I want to visualize, see what's going on. We already have the solve plot, and the solver is given here as an argument, and it's checked against VFI, but we can also check it against elif time eater, and if it is time eater, let's call time eater for the solver. By the way, here we are also setting the solver func directly as a reference to a particular method in the of the object, and then we're calling the solver func somewhere over here. So now if I want to say, let me copy this line. Solve plot, and the solver would be time eater. Now I'm going to get the visualization, hopefully, but something didn't work. Non-type object is not subscriptable. Okay, so we are in that situation where the absence of value function is starting to hurt us. Okay, so let's make v1 not a none, but say zeros of the size and grid. And I guess we can move this out to after we've converged. And do it again. V1 is referenced before assignment. Okay, yes, because that's the callback. It's referenced in the callback. So let's move it up here. It's going to work now. Yeah. See, it's solving. Well, we don't get anything for the value function because we're not computing it. But we are getting this policy function, and now I guess it's time to compare it to the previous solver. This is the time iteration. And, oh, we can already see that it takes more iterations to solve it with VFI. And this is the VFI with continuous Bellman. Do we get the same policy function in the end? So it's starting to sort of go off the 45-degree line at around 1 and goes to 2 and between 2 and 3, closer to 3. It seems to be very similar. And as you can see, it converged within fewer number of iterations. Okay, well, that's good news. That's really nice. I do want to compare value functions, though. It would be nice to have the same equivalent calculation for the time iteration as well, and it's not too hard to do. So let's add that before we move on. But then, of course, we can compare once we write the accuracy check, which is the next thing on our list. The iteration time iteration solver and accuracy measurement. Then we can actually compare by putting a number on the accuracy of these different solutions. Okay, how do we deal with the calculation of the value function? Well, let's look at Bellman here. You know, this is essentially what we need to do, right? So once we have found the optimal consumption level for a particular point in the state space, then we can just plug it into the right-hand side of the Bellman operator or the Bellman equation and calculate without doing any maximization, because we already found the optimal consumption. We can calculate the value for that point. So let's do that, and it's not going to be too much of an additional things to do here. So over here, once we've calculated the CI, C1 of I want to add V1 of I to be equal to something. And the way it's, I have to be careful here because this if else doesn't have to do anything with V1. Okay, and what do we have to do to? Well, first we have to calculate. Oh, what is this cell quad P? Right. The next period wealth. The next period wealth will be calculated with M and C1 of I, which we just found, the optimal one. Then inter F. Where does inter F come from? Inter F is the interpolation function for V naught. Okay, so we need this component as well. And V naught will be updated. Okay. Self-grid V naught. So suddenly we need the V naught as well. And I guess we need to carry it through in the iteration. Let me do Pythonian way as well again. V naught and V1 will become V naught in the next iteration. Okay, so here's the interpolation of the V function from the previous iteration. So interfunc now can be applied to M1, and this is going to be the value function in the next period wealth. Then we have to do the dot product to calculate the expected value function at the scalar. Yes, it is going to be a scalar. And then self-utility of C, well, instead of C, we have C1 of I plus self-beta EV. That all seems to be okay. Now, instead of returning minus mx, we can just equalize it to the, or save it into the, as an element of V1 vector, and V is capital, actually. Okay, so this is the calculation and found optimal consumption, C1 of I. Okay, is this enough? V0 must be initialized, and now let's keep these two in sync. So we can initialize V0 as utility of self of grid. So it's like we're assuming everything on the initial V. V1 is zeros. We don't need this anymore, but we do need to allocate space for V1, the same amount of space as for C, so that then we can access its elements here. Okay. And we're still yeah, I think it should be fine. It should be it. Let's check. Of course, there are errors. It's very seldom that you write everything correctly from the first try. Index 10 is out of bounds for axis 0 with size 10. And where's this? This is our V1 of I. I think there are some, yeah, I'm just using the same variable name, which is not good. By the way, is M1 unique here? Yep. Let's just call this V, and then V is going to be the EV, and V1 of, so the confusion comes from the fact that I'm using 1, like M1, to denote the next period things, like next period wealth or next period value. But I'm also denoting V1 is the iteration, sort of the next iteration in the successive approximation algorithm. So that's why we have a conflicting names. Now it seems to be working. Okay, let's see. And we got the value functions, and they converge as well. Although now we are not tracking the convergence in the value function space, right? We're tracking convergence in the policy function space over here. And again, the time iteration converges in the fewer number of iterations compared to these, but the value function, is it the same? It goes up to 5 and something. Yeah, I think it's the same, or at least it looks very, very similar. Wonderful. Wonderful. So one thing that I want to note in the end is that, look, this interfunc is computing the interpolation function for the previous iteration V0, but we have to do the same for the policy function, and it's not changing before we actually loop through the iteration. But we are, if we look at it, we are passing to the early residual. We are passing C0, which is just a vector, and we are calling this interpolation routine over here. Right, it's the same as this one, but we are interpolating the policy function. Well, the early residual is the equation that we're solving, and every time we're calling the equation, we are interpolating the same function over and over and over again. And this is, of course, inefficient. Let's move it out, and let's do it the same way as we're doing it here. and we can say maybe C not inter for the interpolation, and just interpolate C naught once in here. Interpolation function for policy C naught. Allocate space for policy and value functions. Constraint region, or should I just say corner solution in here? So this interpolation can happen once in the iteration of the algorithm, because C naught is going to be updated here, and then it's interpolated again. And then we can use this C naught as instead of, we can use C naught inter instead of C naught when we call the early residual. But then in the early residual, we should treat this policy as the interpolation function. And then we can just skip this, right? And instead of inter, we're just saying policy here. Because policy already is the interpolating function that we are passing to the early residual, and then we can apply it. Okay, and this way we are only interpolating once in the iteration, not every time we're calling the equation as brand Q is running. Let's check that nothing is broken. And it shouldn't be. I think we've done everything right. And this way we're done with time iteration solver. Oh, one more thing that I wanted to add is when we save the solution to the object itself, let's mention what produced the solution. So solver time, capital small letters, time iterations. If it's produced by the time iterations, and if it's produced by VFI, then we can say VFI here. VFI can be with the different Bellman equation. Let's add that. VFI format. How do we distinguish between Bellman equations? Well, remember we have the property Bellman type, and we are returning the help from Bellman. Well, let's actually return a word, discretized or continuous. Yeah, let's create this internal property Bellman type, and let's just call it, okay, this is what we should return. And here we should save it. Okay, then here we can say here in the solver self Bellman type. Let's see if it works. And we can also update the wrapper function. right now that we have that information. It says here the model is solved if has a solution. Oh, it's solved, so it's not solved. Yeah, well, let's not bother about that. So if the model is solved, then we can also say M solution. Okay, and the solution is, of course, a bunch of numbers. Value, solver time iterations. Solver V5 with continuous Bellman. Yeah, what I meant was to say solutions method. Policy solver, not the method solver. All right, so we're done with time iterations. What's left to do is the accuracy check. And the accuracy check should be a separate method, okay? And I was thinking that similar to the simulator. Where's the simulator? I think we can put it next to the simulator because it's going to be very similar. It's going to compute the average squared Euler residuals for the solution, for the saved solution, should I say. So the idea is that we can use the solution already stored in the object, and to do that we can assert similarly to what we did in the simulator, whether the solution is solved. Need to solve the model to compute the accuracy measure. Okay, and so how are we going to do it, and what are the arguments? Remember I mentioned that the accuracy measure should be done on the denser grid than the state grid, just to make sure that we are actually checking the early residuals not only at the points where the model is saved or solved, but also in between those points. So let's introduce dense grid factor, and by default let it be 10. And the idea is that we can create the grid similarly to what we did with the state grid, somewhere here next to the inits, choice grid, state grid. And we can do the lint space now. Instead of epsilon, we can use the first point of the state grid, m bar, but then the number of grid points, which is also self number of grid points, we can multiply with this dense grid factor. So we are creating a denser grid, and so many times denser. Okay, now the consumption for this grid is going to be given by the policy function that is solved in the solution. And so first we need to interpolate. The interpolation function is going to be the function for the state grid, self-solution policy, interpolation function for policy function. And then we can calculate consumption as inter of grid. So now we've calculated consumption on this dense grid. And I think we are ready to call the early residual. Self early residual with C equals C, M equals grid, and policy equal, is it policy that I need to say? Yes, policy. Well, the policy must be now the interpolated policy function, and that's what we just have here, inter. Now C and M is going to be the same size. It's a one-dimensional array returned by the linspace. So because we've written the early residual function the way we did, that it can work with one-dimensional array, then it should be all fine, and it should return the one-dimensional array of early residuals. So if that's true, then we can calculate the average by, say, invoking NP mean. That's the average of the ER squared. And this is what we should return, right? Maybe we can make a print as well. Just to make it easier for ourselves to call it. Yeah, let's do a verbosity. False by default, but if verbose, then just print. Otherwise, return. And if it's verbose, it just prints, it doesn't return anything. But if we want to make graphs or collect data on accuracy, then we want to keep verbose false. Okay. Accuracy of the solution, and then I want to actually mention what solution that is. How do we know which solution that is? Well, it's solution solver, right? That's what we just coded up, and that was the idea. Is, well, let's not accuracy, but average squared earlier residuals of the solution like this, using so many points, is, and how do we get the number of points? Well, that's this number, and the answer should be this, and we should save it into a variable, I think, to be able to print it here. Okay, I think that's it. Let's say accuracy for both of these solutions, and wait and see. Okay, didn't work. Operands couldn't be broadcast together. That's not good. So something is not working with the next period wealth. Okay, that's probably in the early residual. M1 is MCY. Okay, that's a nasty bug. See, we've prepared the C naught and M naught, but then we're still calling it with M and C. And so it worked because M and C were scalars and they wouldn't change. But now we want them to change. We want them to be a particular shape. See, it's good that we caught it. Time iterations. Why didn't I see the accuracy? Verbose is false. Okay. But at least I didn't see any mistakes. Here's some number, which is probably the accuracy that was computed last. Average squared early residuals of the solution time iterations using 1,000 point is 2 to the 2 times 10 to the power 28. That's pretty terrible accuracy. What do you think is going on? Well, let's comment this out, and then let's say the accuracy, the dense grid factor, let's keep it low. Let me just change the default value really quick. Let's print the ER just to see what's going on. Okay, time iteration. Now, when we calculate accuracy, I guess we don't need this anymore. Here's the problem, right? So we are printing the early residuals, and the first early residual is something times 10 to the power of 15, and then they are quite small after that. So what's the problem? The first point is the point where the wealth is really, really low, and we are consuming everything. We are consuming everything for the very low. For the very low wealth, and remember, we wanted to increase wealth because the marginal value of today's very small consumption, which is the left-hand side of the early equation, is tiny. I'm sorry, it's huge. It's huge. The marginal utility is huge. We want to increase the consumption as much as we can, but there is a limit. That's what it is. Well, it makes me think that because the early residuals are only 0 in the interior solutions, I think we should just exclude all of this early residuals in the constrained region here, where we're consuming everything from the accuracy measure, right? It should probably be measured. Accuracy in that region should probably be measured by something else, not the early residuals. I think that's the way to go. So ER, let me check. NumPy is, there's something about being close. Oh yeah, is close. NumPy is close returns a Boolean array where 2 arrays of elements y is equal within a tolerance. So the way to use it is to say A and B. And so it's true when what? Oh yeah, there we are. When the absolute value difference between the A and B is less than A tol, which is the absolute tolerance, but also the R tol. And it says here that the default A tol is not appropriate for comparing numbers that are much smaller than 1, which is our case. Oh, at least potentially. Okay, so let's is close. A is our C and B is our grid. And now we want to make A tol quite small, smaller than the default. What's the default? 1 to the minus 8. So let's make it 1e to the minus 10. Okay, so this will create a Boolean array of the size of the shape of C n grid. That marks, the C's which are really close to the grid. So this marks the corner solutions, and I just want to say that the residuals is 0 there. So let's say disregard corner solutions. Consumption on the dense grid. Okay, I think that should solve the mysterious huge numbers. Yeah, now we've placed, and see, it replaced the first several points with 0, and that's right, because this is the constraint region. This is where the tolerance shouldn't be there. And now the tolerance level is something on the order of -11. That's pretty good. This is the average. This is the average tolerance. Oh, I'm sorry, the average squared residuals. NP mean of AR squared. Yeah, squared is going to be element by element. That looks a little bit surprising, isn't it? Because the numbers here are on the order of -6, -7. We are including lots of zeros, right? So a lot of the zeros bring this down. So maybe we should take not the mean, but the mean without the zeros. That would be more appropriate. So let's just say that ER equals ER of the points which are not close. Can't I just do that? Okay, we need the NP logical not to do the element by element. So we want to flip these is close, all close, equal none false. Okay, that should do the trick. And still it's on the order of -11. No, it bothers me. Oh, okay, so we are looking at the error residuals, of course, and we're calculating the mean squared ones. So it should actually be totally fine. Yeah, it should be on the order of -11. Okay, so I think this is done. And let's compare the accuracy of different solvers. So this is continuous Bellman. What about time iterations? Solve plot and then sims. Just to make sure we get the same simulations. That's actually a good way to compare solutions as well. See, when we simulate, we're fixing the seeds. So both of the solutions will be used with the same sequence of random numbers. So we should expect to get exactly identical simulations. You can see whether these graphs are the same in all respects. And comparing time iterations accuracy, right? 2 to the 10 to the -11, and then why is this using 100 points? And this is using 100 points because I've changed this dense factor. Which is not right. We should check accuracy on the dense agreed. Okay, here are new results. 1,000 points is what, about 2 times 10 to the -5 for the time iterations, and 2.4 10 to the minus 5 for the VFI with continuous Bellman. So clearly, time iterations produce a more accurate result, more accurate solution. What about the simulated wealth trajectories? Are they the same? They look pretty... Yeah, they look pretty much the same to me. Well, let's, for comparison, let's add a third solver with the Bellman type discrete or discretized. And by the way, I'm not reinitializing the model, right? I'm just changing the Bellman type to discretized. And what it's going to do, because we have this reactive properties, as I'm changing Bellman type, this is going to be the setter. If it's discretized, then the self-Bellman will be updated immediately. And then I can recalculate. Let me skip the sims. Just the accuracies. So about 1.9 times 10 to the minus 5 for the time iteration. For the continuous Bellman, what, 2.4 times 10 to the minus 5. Did you see that the discretized Bellman produced the result in a blink without spending any time like the continuous Bellman did? But the accuracy is only, 0.04. So several magnitudes, order of magnitudes lower or worse, right, than the accuracy of the time iteration and the continuous Bellman solver. Okay, so now, and you can see it's visibly worse, right, than this line or this line. But remember, we are using the same number of points in the state space, the same size of the grid. Of course, we could increase the number of the points on the choice grid for the discretized Bellman and spend a little bit more time, maybe spend the amount of time closer to the continuous Bellman and get a better, more accurate solution. And that's the trade-off, of course, accuracy versus time. Let's make sure that all of these solvers work for the consumption eating problem. I'm sorry, the cake eating problem. The solver time iteration, accuracy, simulator. Let's do the simulator this time. And then discretized as well. Okay, so we're getting the divide by zero warning in the time iteration solver. But the solution produced is looking really, really well. And you can see that there are no artifacts that we used to have in the simulations. That would be nice to figure out where does that fire. I guess eventually, somewhere we're calculating the marginal utility of zero consumption. That must be it. Now, what about the accuracy? The time iteration is producing really nice, accurate solution again, but the accuracy of even the continuous Bellman is much worse. And you can see some artifacts here. And even worse for the, well, they are on the same order of magnitude actually, for the VFI. What's the difference here? Well, see, for the small values of wealth in the cake eating problem, or I should say it this way, because there's no income, then the solution for the small values of wealth is a lot more influential. right? Because a lot of the times that's the really small size of the cake that matters. But here the value function is really curvy, and so the interpolation scheme that we're using is going to have a big effect on the accuracy of the solution. Whereas for the time iterations, we are interpolating the policy function, and the policy function in the cake-eating problem is especially simple one to interpolate because it's linear, right? So interpolating these linear functions is so much easier than interpolating the value function, especially in the region where it's really concave. And therefore, time iterations in this particular model, in this particular problem, become a lot more accurate than the value function iteration. Okay, these are the solutions that we kept for checking. I guess I can remove them now. And this is the notebook that will be saved in the lectures repo. We will come back to the class Deaton and expand it even more when we learn about the other solution methods that exist. Okay, that was a long video. What is it, over 2 hours? But I hope it was helpful. As you know, I was trying to go through the coding process and the thinking process of creating this code. This is going to be a nice code, you know, that you can use later and definitely useful for the exam. So please study it carefully and make sure that you understand everything that's going on here. And I hope that this long and detailed explanation would help you achieve that. See you in the next video.